Okay. Hi, everyone. Welcome to the third review session, I believe. Today is the 18th, and today we are going to be primarily talking about node voltage, which hopefully you all are pretty familiar with at this point. It was on the homework, and I believe she's been talking about it in class. She might have even told you that this quiz will be on node voltage. So, as a refresher, node voltage is basically a method for solving circuits, method for solving circuits using KCL. Keep in mind that's the current law, but we do it at nodes to solve for voltages. So that's the name. That's where it comes from. Um, I'll go over like one thing real quick, and then I'll just kind of get into solving practice problems because hopefully you all are familiar with the method. It's always just, I know it's the most useful for me to just kind of do it over and over again. So, main thing I want to go over is how we are going to be writing these equations. So, let's say we have something like this. I'm just going to do a lot of things here so that like you can look at this circuit, and I'm just doing this so that I can make sure you all are familiar with the sign convention that I want to be using. So let's say we are focusing on this node, right? And we want to think about, okay, what are all the currents going in and out of this node? So what I say here is that in most cases, it is best to try to always assume that the currents are going out for resistors because it'll make your math easier. Um, if you have a current source, such as this or this, you can't necessarily do that because the current source is telling you directly which way it's going. So for here, it would be like that. And keep in mind, this is all one node here, right? For this node, you'd have a current going in, and then this you can say is going out. And the reason that I care about this is because remember, currents out are positive, and currents in are negative. So that's the reason that we do this is because then we can basically have all of our currents be out, meaning they're positive, which makes our math look nice, unless it's a current source. If it's a current source and it's going in, then that's kind of going to be the only situation where your terms are negative. Just wanted to touch on that. Now I think I'm just going to do practice problems, and as I come up to points that I think I should mention, I will pause and talk about those. So, to get started, I will go over a question that looks pretty complex, but is probably the kind of thing you could have on a quiz. So this question, I will take like half a minute to draw the circuit here. Give me a minute. 5 amps, 3 amps, 5 ohms, 12 volts, 4 ohms, 2 ohms, 2 ohms, 3 ohms, and 7 ohms. So in this question, it is saying simply write, you don't have to solve for anything, just write all the equations to solve for the current through the 3 ohm resistor. So you're trying to find this current, and we want to write all the equations that you need to solve for that. So to start, as with all node voltage stuff, we want to start by labeling ground. Ground, again, is 0 volts. It's what you're referencing all your voltages to. We do it with this little symbol or this little symbol, depending on what you want to use. It really does not matter. Technically, like this one is a bit more correct, but this one, if this one refers to like earth ground, so like when your house has a grounding rod, that's what this is. This one is just like a more generic 0 volts, I'm pretty sure. So generally for this class, the circuits will be drawn such that it'll be pretty obvious that it's usually going to be at the bottom. The the general rule is you want to pick the node that has as many components connected to it as possible. So in this circuit, actually, there's kind of 3 or 4 different locations that could even be better, but kind of just for simplicity's sake, I tend to choose the one on the bottom of the circuit just because it makes it look nicer. So like here, right, for this node here, we have 1, 2, 3, 4 components connected to it. Uh, 4 components connected to it. Whereas if we had chosen like this point or this point, right, those also have a lot of components connected to it. However, I'm just going to pick the bottom one because it makes the most sense in my brain, having 0 be at the bottom. So then we have to label our nodes. So the nodes, again, are where you have more than 2 components connected to each other. What that means is that if we had a path like say, for example, we had another thing that was like this would not be a node because there's only 2 components. So what this means is that we basically pick anywhere we have a junction of multiple things. So that would be here, here, and here. Keep in mind, since this is all connected by a wire, this is all one node. So you can label this all like V1, which is exactly what I'll do. So let's say this is V1, this is V2, and this is V3, right? And again, this is all one node, right? All of this has that voltage of V3. This one is V2. This one's very straightforward. This one's V1. And yeah. So then for node voltage, we just do the KCL equations. And that's kind of it. The point of this is that you get 3 equations and 3 unknowns, and then that's enough to solve for the values. If you have 3 equations and 3 unknowns, you can plug it into your favorite equation solver and it'll do it. Or you can do the math yourself, I suppose. But anyway, let's just do that. So V1. At V1, we want to look at it's good practice to kind of draw what you're defining all these currents as. So this one we can't pick going in unless you wanted to. Yeah, like you just can't really do that with the current source because the current source is telling you what direction the current is flowing. But with anything with a resistor, we can kind of just say it's flowing out and that'll let us use a positive number. So going down first, we have V1 minus 12 volts over 2 ohms. Again, this is just from if we know V equals IR, then I equals V over R, where this voltage is the difference in voltage between the 2 sides of the resistor. So if we're kind of guessing that the current's flowing this way, then it would be this voltage minus this voltage over the resistance. So that's V1 minus 12 volts over 2 ohms. We know that this point is 12 volts because since we've defined this as 0 volts, and we have 12 volts here, this is saying that from this side to this side, there is a 12-volt difference. So if we have 0 volts here, we go up 12 volts, then we are at 12 volts here. That's why we can say that. So that's current going down. Then the current going to the right through that 4 ohm would be V1 minus V2 over 4. I'm not going to write the units because it'll get kind of annoying. And hopefully you all can see that. Next, with that 5 ohm resistor, it would be V1 minus V3 over 5. And then at the top there, we would have minus 3 amps because it's going in, and that all equals 0. One thing I will point out, if you want to double check that you're writing your terms right, make sure that you do actually, like I know I just said I'm not going to write the units because I don't want to, but if you do have the units in, you should have a voltage over a resistance because since this is KCL, right? Remember, KCL is I1 plus I2 plus I3, so on equals 0. All of these terms are currents. If you're thinking about this in like you're doing physics class and you're thinking about units a lot, all of these should evaluate to a current. And in this case, they do. So you can double check that to make sure you're doing it right. I've seen some very, very creative ways that people have tried to do this, and if they had checked their units, they would not have made those mistakes. Next up, at V2, I'll label this as well. Going to say out, out, and out. So at V2 then, we have V2 minus V1 over 4 plus V2 minus 0 over 2 plus V2 minus V3 over 7 equals 0, and that's it. Finally, at V3, we have, again, for all the resistors, I will say they're out. However, we have currents here, so we can't just kind of say those. We have to just do what they say. You have to follow them. So for V3, starting with that 5 amp source, it's going in, so we have minus 5 amps, or minus 5. And then with the 3 ohm resistor, we have plus V3 minus 0 over 3, plus V3 minus V2 over 7, plus V3 minus V1 over 5, and then plus 3 amps from that top one, because that's going out. And then, so these would be our 3 node voltage equations. And then keep in mind when you have a question that tells you to find a specific thing and is telling you to write all the equations, it'd be a good idea to also write down that last equation, right? So then the last equation here, if we're trying to find the current through that 3 ohm resistor, we could really just say I 3 ohms equals, well, it's going to be the current going here, which is going to be V3 over 3 ohms, pretty much. Or you could be explicit and say V3 minus 0 over 3 ohms, the same way that we did it right here. And that's how you do a question like that. One thing I will point out is that if you look, right, because we made all these arrows pointing out of the nodes, you always have for the V1 equation, you're always going to have V1 in the first term. And for the V2 equation, you're always going to have V2 in the first term. For the V3 equation, you're always having V3 in the first term. So like when I'm grading these, I look and just see, did people do that right? If so, then they get the points. One thing I will also point out is that if you do want to, if it doesn't make sense in your brain to have like one of the arrows pointing to the left and one of them pointing to the right, you want them both to be pointing in the same direction. So let's say you did like V1 pointing to the right here, and then you said V2 was also pointing to the right. So let's say you did it like that on that specific one. So in this case, we'd be affecting this term, right? So now what this would turn into for the V2 equation is it would be negative because it's going in, and it would be V1 minus V2 over 4. What I'll point out here is that this is mathematically equivalent to V2 minus V1 over 4. So this is just going to show it like doesn't matter which one you pick. And also, again, when I'm grading, I just look, okay, if there's a negative sign, I look to see if it's in the second position. And if it's there, then it's correct. So, just make sure you like know what you're doing here because it will make your life easier. It'll make my life easier. So yeah, that's how you do that question. And then like if this was on a quiz, this is just your final answer. It's these 4 equations. And if you know how to write these equations, then you can solve the circuit. This isn't an algebra class, even if there is a lot of algebra. The class is making sure that you understand the modeling of a circuit. And yeah, now I will do more questions because we have so much time. Next up, this one's quite a bit simpler, but it is still a node voltage question. That's blue. I want black here. Okay. Okay, so this question is saying use node voltage to find power of that dependent source, which I'll just label as that. And it's the power associated with it. So it could be positive or negative, we don't know yet. Um, so again, same way we've done before. We start by labeling what we want to be 0 volts. I'm going to say the bottom part is 0 volts. And then we label our nodes. So again, the nodes are the points where there's more than two components touching, so it's like a junction. Here, we actually only have one node, which is fine. We just only have one equation. And basically, we're just doing a KCL equation here. And with it, you can basically the only difference between this and like doing KCL in the first week of the class is that now we've defined 0 volts, so it makes our life a lot easier. So if we have V1 here, then we can write our equation, right? So looking out to the left, we would have V1 minus 9 volts over 20 ohms. To the bottom, we'd have V1 minus VA over 2 for the same reason I described on this page with 0 volts and 12 volts. Here we have 0 volts at the bottom, and then it goes up to VA over 2. And you can just write that in there. And that over 10 ohms. And then plus V1 minus 0 over 40 for that right part. And that equals 0. However, if you look at this, this is not quite a solvable equation because we have two variables and one unknown. We have this VA. So you would have to write out what VA is. Based on the defined VA, so notice that the plus is on the left and the minus is on the right, that's telling us that VA would be equal to 9 minus V1. Cool? Makes sense? I hope. Yeah, because if it's higher on this side and lower on this side, just by the definition of VA, right, then that would be what you're looking for here. So even though we said this here, that's because we defined the current as going that way. If we have 9 minus V1, that's the VA that we have there. Yeah, make sure you get your signs right, even if it can be a bit confusing. So now we have two equations and two unknowns, we can actually solve this. So if we plug our stuff in, let's see. First, let's start by simplifying this equation here. So if we multiply everything by 40, which is the highest common factor, or lowest common factor, that's the word, we get 2V1 minus 18 plus 4V1 minus 2VA plus just V1 equals 0. And then we have combine all the V1s, you'd get 1, 2, 3, 4, 5, 6, 7 V1 minus 2 VA equals 18. Then if we plug this in, we'd get 7 V1 minus 2 times 9 minus V1 equals 18. So then we have 7 minus 9, or no, not that at all. 7 minus 7V1 minus 2V1, so that's going to be 5V1 minus 18 equals 18. Then we have, make sure I'm doing this right. Might have messed up. Oh, yeah, I messed this up. Okay, because this is, we have a minus and a minus, so this becomes a, I'll just write out the intermediary step. 7V1 minus 18 plus 2V1, right? And then we have 9V1 equals 36, V1 equals 36 over 9. Wow. So now we know that voltage. And now what can we do with that? Well, from this, we know that VA equals 9 minus 36 over 9. And that would be, well, 36 over 9. I don't know why I left it like that. That's just 4. And then VA equals 9 minus 4, which is 5. You look at that. So then we're very close to finding the thing we want. If we remember, this means we need the current and the voltage. The voltage is going to be just VA over 2, and we know that now. VA over 2 is just going to be 2.5 because we know VA, right? And then the current we can now find because we know V1 and we know VA. It's just the current through that 10 ohm resistor, right? So I kind of lost track of the order of my work here, but I is going to be V1 minus VA over 2 over 10, which in this case is going to be 9 minus 2.5 over 10, which is going to end up getting us 0.15 amps. I'll move, I'll just do it at the bottom here. So now, if I draw this back on the circuit then, we know that we have from here to here, we have 2.5 volts, and we know that going down, because again, we defined this as going down when we just solved this equation, we have 0.15 amps flowing this way. And if we think back to our passive sign convention, we have the voltage drop in the same direction as the current, meaning that this is positive power, which is meaning that this is actually dissipating power. Even though it's a voltage source, it is like it's absorbing power. It's putting it off as heat like a resistor would. So what we all get is that the power of this thing is equal to 0.15 times 2.5, which will get us 0.375 watts. And that would be your final answer for this question. So again, the process for this was we labeled something as 0 volts. We did a single node voltage equation. And then once we had this voltage, we could find basically everything else about the circuit. We found VA, then we found the voltage, and then once we knew the voltage, we could find the current, and then we multiplied them together to get the power. And yeah. Okay. Next up, now I will do another question that has just writing equations. And I'll take another couple, like another minute to draw out this really big circuit. Okay, so the goal here is to find this Vx. So write equations to solve for Vx. Don't actually have to solve, just have to write the equations, just like we did with this question. Okay, so let's look at what our nodes would be. Or first, of course, actually, we want to define 0 volts. As I said before, you want to define 0 volts as where the most components meet, which in this case, again, shockingly, is just the bottom. There's like 1, 2, 3, 4, 5. Very cool. So we have a lot of things that we can just say are 0 volts. Next up are actual nodes. So we're going to have one here, and if we note, these 2 points are connected, so this is all V1. Next up, V2 and V3. And now we're going to do the exact same thing as we did before, and this time I'll do it fast. So we have V1, and V1 coming in from that left side is going to be negative 5 I naught because it's coming in, so it's negative, plus V1 minus 0 over 20. That's from this part. then to the right, we have plus V1 minus V2 over 5. And that all equals 0. Then for V2, we have V2 minus V1 over 5. That's going to the left. Then we have plus V2 minus 0 over 40. That's going down. And then we have plus V2 minus V3 over 10. That's going to the right. That's all three sides, so that's it, equals 0. And then at V3, going to the left, we have V3 minus V2 over 10. Going down, we have V3 minus 11 I naught, because we have that voltage source down there, over 5. And then to the right, we have V3 minus 96 over 4. And that equals 0. Then we're almost there. However, there's still two more equations we need to write. First off, this right here is 3 equations for unknowns because we haven't defined I naught, right? So we have to say, okay, I naught is going to be, it's just whatever we found was this. And so on the V2 term, that was this equation. So we can just write that there. V2 minus 0 over 40. So now we have 4 equations for unknowns. But then the question was explicitly asking for solving for Vx. And Vx, if we look at this, okay, if we know if it's the difference between this point and this point, and we know that this point is 0 and this point is V1, right? It's going to be V1 minus 0. So we can just say Vx equals V1. And that would be the whole question. So if you get a question like this on your quiz tomorrow, hopefully after seeing me do all these examples, you'll be able to do it pretty quick. Okay. Here is another question. This again, we're going to actually be solving for a power. Oops, got a pencil. Okay. Mhm. And then we want to find the power of the 7 ohm resistor. So for this, if you remember your power equations, that means we're either going to want to find the current and the voltage, or with the resistor, since current and our voltage are related directly, it's also I squared times R or V squared over R. So if you find either the voltage or the current, you can just solve it. So, and before we even get there, so the 7 ohm resistor, actually I'll get there later. Yeah. So water. Okay. So just like always, we're going to start by labeling what is ground. Again, it is the point on the bottom in this case, because we have so many things connected to that point, and also because it looks nice. You can put anything as ground and you'll always get the same answer. It just might make your work easier or harder depending on what you do. And now we want to look at where are the nodes. Here, we have a node here, right? But if we look, actually this whole thing is just one node because it's all connected by a wire. So for labeling our nodes, we basically have V1 and it's this whole top part. When I have graded questions like this in the past, I've seen people try to label this V1, V2, and V3, and they get very confused when they go to write this part of the node voltage equation because there's no resistor. And they get very creative with how they are trying to do that. So don't be like that. Acknowledge that since everything is connected by a wire, it all has the same voltage. So that's all V1. And then if we're looking at the currents with the resistors, we can say they're all going out. With this one, we can also say it's going out. We're just going to think of this as V1 plus 60, right? Hopefully you can see that because we have V1 here. It's going to be V1 plus 60 there. So it's still going out. Here, it has to be going in, out, and out. And then we just write our one equation for that. So V1 is going to equal to, okay, V1 minus 120 on the left over 20. And then we have V1 plus 60 minus 0, right? Because we're looking at this point and this point. And then that over 5. And then minus 36. And then plus V1 minus 0 over 4. And then plus V1 minus 0 over, and then I'm just going to say 3 plus 7, right? Because that's accounting for this whole branch. You just think of those two as being in series. So that all equals 0. And I'll even just rewrite this as 10 because that makes my life easier. Okay, so one thing I'll note is that the current through that 7 ohm resistor, which I said we could find here to find the power, is going to be this term, right? Because this term was related to this current here. And since current is the same everywhere along the path, right? If we find it, then that'll be that current. So that's our goal. Basically, that just means we have to find V1. And then it's going to be V1 over 10. And then we multiply that squared and then times the resistance and we'll get our answer. So let's solve this. The lowest common multiple, multiply everything by 20. So if we multiply everything by 20, this is not equals, it's just the V1 equation. Okay. So multiply everything by 20. Going to get V1 minus 120 plus V1. So if you multiply by 20, it'll be 4V1 plus 240. Yes. And then minus 36 times 20. I'm not even gonna, actually I can do that in my head. 720. I'm so good at math. Then plus 5V1, and then plus, this is going to be 2V1 equals 0. Yeah. So then if we move things around, we have, okay, we got 1V1, 4V1, 5V1, 2V1, 5, 10, 12. So we got 12V1, and then minus 120, minus 720. What is this? This, and this. What is that going to add up to? Negative 600, no. Plus, yeah. Yeah. So if you add that and that, yeah, because, yeah, you end up with 12 volts equals 600. If you were to take all these constants to the other side, yeah, that checks out. And then if we divide by 12, we will get that V1 equals 50 volts, right? So then, as I said earlier, the power through that 7 ohm resistor is going to be I squared times R, where we know I squared is going to be V1 over 10, and then the resistance we already know is 7 ohms. So then that's going to be 50 over 10 squared, sorry, times 7, which is going to be 5 squared times 7, which is 35 times 7, which ultimately gets us 175 watts, which is kind of a lot of power, actually. That's like I don't know, it's probably what your laptop charges with if you have a big laptop, or it's like 3 iMac chargers, or 3 MacBook chargers, I think. But yeah, that's how you do that question. So just as with all the other questions I've been going over, right? Label the zero, label the node, write the equation, do the algebra, and get your answer. Okay, so I've done 4 questions now. Do like 1 or 2 more. Might end this one a bit early just because I don't know. There's not too much to go over besides what I've already gone over, to be fair. Um, let's see. Yeah, sure. I'll do this one. More of the same, writing equations. Okay. Gonna label the bottom 0 volts. Oh, and the question is to just just write the node voltage equations. So what are our nodes here? We got 1, 2, and 3, right? All of those are not directly connected to each other, so those are all 3 different voltages. Then I'll point out here, this point here is going to be V2 plus 10, right? So when we're looking at the current through this resistor, we can think of it as this point minus this point, or this point minus this point. Yeah, and this point here is going to be 48 volts. So let's just start writing our equations. At V1, we're going to have going down V1 minus 48 over 5. Then to the right, we have V1 minus V2 over 4. Then coming in from the top, we just have minus 4 amps, right? That all equals 0. For V2, we have V2 minus V1 over 4 plus V2 over 0. Nope, that's not what I meant to say at all. Plus V2 minus 0 over 8. And then to the right, if we're thinking about it going this way through the resistor, it'll be V2 plus 10 minus V3 over 6. And that all equals 0. Then for V3, going up, we have positive 4 amps because it's going out. And then to the left, we're going to have V3 minus, now that same term, that V2 plus 10 over 6. And then going down, we have V3 minus 0 over 10 equals 0. And for this, wow, that's 3 equations, 3 unknowns. You could solve that and get all the values in this circuit. Very fun. Let's see, surely I can find another question that's moderately interesting to do. Um, yeah. So I did that one, I think, right? Did that. Wait, no, I'm looking at the wrong thing. Okay. Okay, yeah, I'll do this one more. So use node voltage to find power associated with all elements. So we want to find the voltage and the current across every element in this circuit using node voltage. So start, label your 0 volt, label your node, again here, one node here. And yeah, so let's write our one equation so we can figure out what V1 is. And then once we have V1, it'll be pretty trivial to figure out the voltage and current for all of these components, right? So real quick, I'll mark, we know we have 12 volts here, right? So that's good. Then at V1, we're going to have minus 1 amp going in, plus V1 minus 0 over 2, plus V1 minus 12 over 5, and that all equals 0. Now we got to multiply by 10 to get rid of all these fractions. So this is going to be minus 10 plus 5V1 plus 2V1 minus 24 equals 0. If we add all this up, we're going to get 7V1 equals 34. And then V1 is going to be equal to 34 over 7, which is roughly 4.86 volts. Now, if we want to find the current and voltage associated with every device, then we just have to look at how those things all relate to V1 pretty much. So we can start with the resistors. Those are kind of easy. So I'll start with that power of the 2 ohm resistor, right? We can just think of this as, remember, we can say this is either IV or V squared over R or I squared times R. And if any of you don't know how we get this, it's just if you take IV and then plug in V equals IR, right? If we plug this into here, then you'll get I times IR, and then that's how you get that. Likewise, if you plugged in I equals V over R, then you'd get that P equals V over R times V, which is, okay. Little tangent, but if anyone just was wondering where those numbers came from, that's how that works. And that only works for resistors because resistors are the only things that really have that V over R relation or V equals IR relationship. So for this one, since we already have voltages, I'm just going to use V squared over R. So for this 2 ohm resistor, the voltage is just going to be V1 minus 0 squared over R. And that's going to be 4.86 squared over 2, which gets us about 2 point, what is it? Yeah, not 2, not at all 2. Yeah, 11.81 watts. For resistors, you never really have to think about if it's positive or negative. For a resistor, it should always be positive because you can't have a sorry, water. You can't have a resistor generate power. That wouldn't really make any sense. For the 5 ohm, let's look at, okay, now that we know that V1 is smaller than 12, we can kind of assume, current flows from high to low voltage. It'll flow to the left there. So then the power of that 5 ohm resistor is going to be 12 minus 4.86 squared over 5, which is going to get us about 10.22 watts. And then for the 1 amp source, well, we know that it has 1 amp flowing through it that way. And then we know that there's 4.86 volts here. If we look here, the voltage rise is in the direction of current, meaning that this is going to be negative. So the power is going to be IV, which is going to be 1 amp times negative 4.86 volts, which is going to be just negative 4.86 watts. And then last but not least, this is the power of the current source. And then last but not least, we have the power of the voltage source. And that we know its voltage, and then its current is going to be the same as the current from this 5 ohm resistor because they're on the same path, right? So the current in that 5 ohm resistor is going to be 12 minus 4.86 over, oh, and before we do this, actually, we should look at the direction. So, right, if we know the current's flowing that way, up here, then it's going to be flowing in the same direction down there. So since, again, the voltage rises in the direction of current, this is going to be a negative power. So we can basically, I'm just going to ignore the sign until the end and then just put it in as negative. But the current there is going to be 12 minus 4.86, which is V1, over 5. So this is I, and then times the voltage, which is 12. And that would get you negative 17.16 watts. And then if we look, if we were to add these numbers all up, that's horrendous. Hold up. I can't draw a squiggly bracket. There we go. The sum of all these powers does actually sum to 0, which kind of tells you that you did it right, because all the power produced is also all the power consumed. And yeah, cool. I think that's all I'm gonna do. I only have like there's still like 15 minutes left, but there's not really much more I could go over, so I'm gonna end it here. Yeah. Good luck on your quiz tomorrow. Bye bye.